Welcome and greetings from Boulder, Colorado. I'm Stephen Varan at the Institute for Telecommunication Sciences. I want to thank you for your interest and thank the organizers of QUOMEX 2021 for making it possible for us to share our work in spite of the global pandemic. I'm presenting my paper, Measuring Speech Quality of System Input while Observing Only System Output. This is a short paper. And as such, I have a very limited time to present. I won't even be able to speak to all of the slides that I've prepared. My goal is to motivate you to look at the slides more later on and to read the paper. Please do feel free to contact me with any questions, comments, input. So we have a system under test. Speech goes in, that's reference speech R, and speech comes out, that's test speech T. We can assess the quality using subjective testing. Or we can build no reference estimators to assess the quality. We can train those from our subjective test results. If we use machine learning, which is a great idea because it's very powerful, we will need a lot of data, perhaps more than is available subjective test-wise. So we can train from full reference estimators, and we have successfully done this. The resulting estimates then are great, except that we have a situation sometimes where the input speech is not actually the studio quality input speech that we would like. It's not R, it's R hat. Okay, it's been corrupted by some noise, some reverberation, etc. because recordings that form the databases that are available just aren't perfect. And what that means is that we have not absolute quality out here, but we have relative quality. And if we could move this connection over here, then we would have absolute quality. But in reality, things to the left of this line generally won't be available, and we are, in fact, stuck with relative quality. So the issue here is about training no reference estimators using full reference estimators when speech is imperfect. And this is also the issue of absolute versus relative speech quality. This motivated me to set up this experiment. Processor that produces some distortions that we'll discuss later, and system under test. So we go from studio quality speech to what you might call field quality speech, and then the output. And I asked, could I make a no reference estimator that could be trained from full reference estimators to produce the input speech quality? And for completeness, I also did the same for relative quality and for absolute quality. In each case, building a no reference estimator, training it from a full reference estimator. Some details: I used wideband speech, 3-second segments, 4 different full reference estimators in order to get a good breadth of results. The processor added heating, ventilating, and air conditioning noise, which is prevalent, reverberation. The filtering was low frequency boost and cut and high frequency boost and cut. So mixed these together to get wide variation and retained the files where the quality was in the upper half of the scale. This resulted in on the order of 10,000 speech files used in this work. The systems under test are wideband speech codecs, so AMR wideband, EVS, and Opus, 3 different bit rates for each. And there's a line here on the variation introduced by the processor versus what's introduced by the SUT. It depends on which estimator you're using. The no reference estimator is very simple, using statistics from mel-frequency Kestrel coefficients and then some fully connected layers and ReLUs to get down to a single quality estimate. The notion here is that by doing something very simple and unoptimized, I get proof of concept. If one were to work on this more and do something more thoughtful and optimized, I believe one would get even better results. But we have the answer that even with very simple network, one can train a no reference estimator to measure input speech quality, even though it can only see the output. Now, the reason is because the input impairments, noise, reverberation, and filtering, are still observable at the output. And while these codecs do change the nature of those and introduce additional impairments, they do remain somewhat distinct from, or the network can distinguish them from the SUT impairments. So what we see here is good correlations between the no reference measure of input quality and the full reference measure of input quality, and perhaps more importantly, no significant drop between the training and the validation. We held out 10% of the files for validation. Similar robustness seen in the RMS error results down below. Is this useful? I argue, of course, that it is. We can have our output quality here, but if we can augment that with input quality, then we know more about what the system under test is actually doing. We can assign blame or not blame, if you will. If we have relative quality, then this input quality provides a path from relative quality to absolute quality. The way that works is by using the notion of additivity of impairments, which goes back to the E model. Very briefly, if we take impairment to be 1 minus quality and we weight and add them up, it turns out that we're weighting and adding up quality values. And we found weights in the full reference domain and transferred them to the no reference domain and found out that we could explain a lot of the variance and get to more absolute no reference estimates. So the answer is yes, we can measure input quality at the output. The case I set up is a special case, but I think it's a common special case. There are some limitations, and there are definitely connections to other work, including multidimensional analysis of quality. Thank you very much for your time today.